final gear retreat here. The gear network was funded in 2011 by NSF, and the first retreat took place at the main hub at UIUC, Illinois, Champaign, and there was both a junior retreat and then after that a retreat. 2014, we had separate events. The junior retreat took place at the University of Michigan, and the retreat took place at the University of Maryland. This time we in fact just finished the third and final junior retreat, and we're into the second week of year stuff. So the thing that really struck me last week, and again, just looking out in the audience, is how many new faces there are in the crowd here. I think it's a real testament to the success of the network program and so on, that we really have a whole new generation, in fact, a whole new couple of generations of mathematicians because of this. Although this event is very much focused towards the future, as I'm sure you all know, it was preceded by the tragic loss of Miriam Mirzakhani. Although we deeply mourn her loss, I'd prefer to think instead of the sort of amazing mathematical and personal legacy that she left us. And with that in mind, I'd like to dedicate this conference to her memory and to that legacy. And to begin this event, I'm actually delighted to have introduced someone who's been with us from the beginning. She was a main participant in the first program at IHP, which Gear played an important role, and then she was one of the organizers of the first junior retreat. And she continues to be a big part of the Gear family. So, further ado, I'd like to introduce Fanny Kassel from IHES. We'll talk about convex projective structures and Anosov.
Thank you very much, Steve. And thank you to all organizers for inviting me. And I would also like to take this opportunity to thank actually Anna, Bill, Richard, and Steve, and the other Steve, for making this network possible and providing me and all of us with so many wonderful mathematical opportunities since 2012 or maybe even 2011. So thank you. So I will be talking about joint work with Jeff Danziger and François Guerito. And so as we all know, the acronym GEAR means geometric structures and representation varieties. So in this talk, I want to talk about some specific geometric structures and some specific representations and make some links between them. So more specifically, so the geometric structures I will be interested in are real convex projective structures. So what's a convex projective structure on a manifold M? That's just an identification of M with a quotient, omega mod gamma, where omega is an open subset of real projective space that's properly convex. And properly convex just means convex and bounded in some affine chart. And gamma is a discrete subgroup of projective transformations that preserves omega. And the big question, would be to find and study nice classes of such structures. And more specifically, today I would like to focus on the point of view of discrete groups. So find nice classes of such discrete groups gamma. So that's the very, very big goal. So in order to do this, what we can do is first focus on the main fundamental example, which is real hyperbolic geometry. So we can see the real hyperbolic space, Hn, in its projective model. So where a quadratic form signature N1 is negative. And then this is an open subset of projective space, which is properly convex, because in some appropriate affine chart, it is just an open ball. And then, in this case, so we take omega equals this, and gamma is a discrete group of isometries of Hn. Or in other words, it belongs to PON1. So ON1, 1 plus or minus 1. Okay, so in this very classical setting, we know several very good classes of discrete groups. So maybe the first class is the uniform lattices. So gamma such that Hn mod gamma is compact. That's one very nice class. Another very nice class is the non-uniform lattices. For which Hn mod gamma is non-compact but with finite volume, so we allow now cusps. Then there's a larger class that contains all the uniform lattices. That's the so-called convex co-compact groups. So here we don't allow cusps, but we allow funnels. And then there's an even larger class, which is the class of geometrically finite groups. Where we allow both cusps and funnels. Okay, and today I will mainly be focusing on the left part of the picture. So maybe I should first recall the formal definition of convex co-compact and give some examples. So the definition, so a discrete subgroup gamma of isometries of Hn is convex co-compact. And I will denote this in the whole talk by CC if there exists a closed convex gamma invariant subsets of Hn such that the quotient is compact. Or equivalently, what I will denote by C gamma Hn mod gamma is compact. Where the C gamma Hn is just the convex hull in Hn of the limit set of gamma in the boundary of Hn. And what's the limit set? as we know, the limit set is the set of accumulation points of some gamma orbit, so of gamma x for some x in Hn. And it does not depend on x. Okay. And now just to recall and make sure we're all on the same page. So maybe two very classical examples of such groups is maybe first Schottky groups. So, okay, so this is H2 in the projective model. And we can take pairs of pairwise disjoint half spaces, and then take some hyperbolic elements. Here, gamma 1 that sends the complement of this half space inside this half space, and maybe here another one, gamma 2, that sends the complement of this half space inside this half space, and then we can take the group generated by these gamma i's. So if we look at all the translation axes of the elements, they do this. So they accumulate here onto the limit set. Which is a counter set. And then here it defines convex subset of Hn, which is exactly my C gamma H2. So this is the smallest possible such set. So we want to call it the convex core. And the action of gamma on this C gamma H2 is indeed co-compact, because this here is a compact fundamental domain. Okay. So that's one first very classical example. Another example would be quasifunction groups. Which are continuous deformations of taking a surface group, embedding it into the isometry group of H2, and then embedding this into the isometry group of H3. And we deform, but we still ask that it preserves a topological circle in the boundary of H3. Okay, so now the picture is like this. Here we have a copy of H2 inside H3, and at first our group preserves this, but as we deform, the circle becomes a quasi-circle, which is the limit set, and we can take the convex hull of the limit set, which is now this C gamma H3, and the action is co-compact. Okay, so we all know this, that's great. So I would just like to make one last comment. There are two nice things about convex compactness. One thing is that it's stable under small deformations. And the second nice thing is that it's the same as gamma being quasi-isometrically embedded. So maybe I just recall what this is. So gamma, a discrete subgroup of G, a semi-simple Lie group here, PON1, is quasi-isometrically embedded if there exists constants such that in the Riemannian symmetric space, which here is Hn, the distance between our fixed base point and gamma of the base points is at least C times the word length minus C prime. So gamma orbits grow linearly. That's the point. So that's the picture for Hn, and now we would like to have a similar picture, but in this more general setting. Okay, so before doing this, maybe I make one preliminary remark, which is that essentially the situation is quite similar to Hn. So if gamma preserves an omega like this, then in fact, as in Hn, it acts by isometries for a nice proper metric called the Hilbert metric. So define it in a very natural way. If this is omega and we want to find the distance between x and y, we just take the projective line passing through x and y. It intersects the boundary of omega in 2 points, and then we just take the distance to be half the log of the cross ratio. And for Hn, this indeed coincides with the usual hyperbolic metric. And so, in particular, if gamma preserves omega, then it acts properly discontinuously. Okay. So in all cases, we have isometries of convex sets, so the situation is kind of similar to this. But the global picture is a little bit more complicated. So now I'm looking at all discrete groups gamma in PGLN plus 1, preserving some omega. And omega is not fixed. It's allowed to vary. Okay, so what's the picture for this? So I'm going to focus on the left part of this picture because it's already interesting and complicated enough. So we have a very large class of groups, which is those that are quasi-isometrically embedded in PGLN plus 1. So this is a natural class of group, except that it's not so nice because it's not stable under small deformations. However, inside we have a much smaller class, but that's very nice, which is the groups gamma that divide some omega. So dividing means that omega mod gamma is compact. And these groups, it's nice because they are stable under small deformation by work of Kassel. And so it's a very nice class of groups that have been studied a lot since the 1960s by many, many authors, in particular Ben-Zekri, Katz-Winberg, Kassel, Goldman, Troy Goldman, Yves Benoit, and many others afterwards. And one interesting feature is actually that there are such groups, gamma, that are Gromov hyperbolic, as in the case of real hyperbolic geometry. But there are also some of them that are not Gromov hyperbolic. And some interesting examples of such groups were constructed by Yves Benoit, and also recently by Ballas, Danziger, Lee, and by Choi, Lee, and Marquis. So, okay, so that's very nice. But now, so the goal for this talk is to kind of fill in the gap in this picture and add some extra classes of groups that could be interesting. So in particular, so the goal would be to find some of convex to compactness in this setting. That would in particular be stable under small deformations. And of course, we want that there are many examples. And we will see that there's not a unique way of doing this, so the situation is a little bit more subtle, maybe, than real hyperbolic geometry. And also, we will be making links with Anosov representations. Okay, so is there any questions so far? Okay, so otherwise, so let me start with this. So first we want to start with some strong notion of convex co-compactness. Oops, sorry. Okay, so what we want to do is go here and just generalize this from Hn to some more general property convex omega. But we will take omega to have a strong property, namely its boundary should not contain any segment. So we now take gamma to be a discrete subgroup of PGLN plus 1. We say that it's strongly convex co-compact. In projective space. If gamma is contained in the isometric group of some omega, with such that the boundary of omega contains no segment, as for each n. So it's so-called strictly convex. And if there exists a closed convex subset now of omega, such that the quotient is compact. Equivalently, C gamma omega mod gamma is compact, where C gamma omega is again the convex hull of the limit set, so the convex core. So here it's the convex hull in omega of the limit sets of gamma in the boundary of omega, which again is the set of accumulation points of some gamma orbits of omega. And again, it's independent of x because of strict convexity. Okay. So that's a nice class of groups. So first, we impose some rather strong condition on omega. So it's kind of normal that we should get some strong property for gamma. So the first strong property that we get for gamma is that, in fact, it's Gromov hyperbolic. So this already follows from the work of Yves Benoit and from the work of Crampon and Marquis. So I should say Crampon and Marquis introduced some strong notion of geometric finiteness. And it turns out that the groups that they introduce, when you restrict them to quasi-isometrically embedded groups, in fact, it is these strongly convex compact groups. So the lemma is that if you're strongly convex compact, then you're Gromov hyperbolic. And maybe I will just give a very short proof of this, just to give you some intuition how the boundary of gamma, I mean the regularity of the boundary of gamma, can affect the properties of the group. So it's enough to prove that C endowed with the Hilbert metric of omega is Gromov hyperbolic, is a metric space, because gamma acts co-compactly on this by isometries. Okay, so suppose not. So here's the picture. We have our omega, and inside we have our set C, on which the action is co-compact. And we assume that C is not Gromov hyperbolic. So this means that there are thicker and thicker triangles. So we can take such a sequence of very, very thick triangles, AK, BK, CK. And in fact, because omega is strictly convex, geodesics for the Hilbert metric are exactly the straight lines. So my triangle really looks like a triangle, like this. Okay, and it's very thick, so it means there exists each time a point xk, such that the distance from xk to the union of the sides AK, BK, and AK, CK goes to infinity. So now we use co-compactness on C. So by co-compactness, we can find gamma k such that gamma k xk remains in some fixed compact subsets of C. And now we can just take subsequences and make everything converge. So up to subsequence, we can have gamma k xk converges to some x in C, gamma k ak converges to some a, gamma k bk converges to some b, gamma k ck converges to some c. And of course, we have C that x belongs to BC. Okay, but so now we use this condition, and this condition implies that actually AB union AC is contained in the boundary of omega, because our metric is proper. But we assume that omega was strictly convex, so it does not contain any non-trivial segment. Therefore, A equals B equals C in the boundary of omega. And so we get a contradiction, because here we have a point which is not in the boundary of omega, but here we see that it is in the boundary of omega, so contradiction. Okay. So that's the first nice property of these groups. So I can draw this class of groups here, let's say. So these are the strongly convex compacts. Okay, and they have more nice properties. So in particular, we prove that they are stable under small deformation. There's a good notion of duality, so you're strongly convex compact in RPN, if and only if you're strongly convex compact in the dual of RPN, so for the action of PGLN plus 1 on the dual projective space. And also, if you're strongly convex compact in projective space of dimension n, then you're strongly convex compact in any bigger, larger projective space. So what do I mean exactly by this? So the point, we have PGLN plus 1, which is here. but PGLN plus 1 is almost the same thing as SL plus or minus n plus 1. And this group now embeds into the larger one, SLN plus 1 plus or minus, which again is almost the same thing as this PGL n plus 1. So what I just mean is if we start with a group gamma that's here, and that's strongly convex to compact, then it can be lifted to a group here that preserves a properly convex cone in Rn plus 1. And then we can embed it here and project it. And then here it's strongly convex to compacted to the larger projective space. OK. And I will explain in a moment why this is true. But first, let me say that this implies already that there are many examples. Because we can start with some known example. So typically, we can take some of these examples with Hn. Then we can embed it into a larger projective space here. And then, with a bit of luck, there are some non-trivial deformations. And we know that after a small deformation, it will still be strongly convex compact. And in fact, I mean, what I just said is exactly what happens here for the quasifunction groups. We take something that's convex compact in RP2, then we embed it in RP3, and we deform. Except that here, for quasifunction, we only deform in the isometry group of H3. But now we could also deform in PGL4 as we wish, and we will still get something convex to compact. Or for free groups, it's even easier. So in particular, to generalize these quasifunction things, what we can do is we can take a group gamma that's convex to compact in POP1, so the group of isometries of HP, and then we can embed POP1 into POPQ plus 1 and deform. And here we actually get many interesting groups from a geometric point of view. So in particular groups that I want to call HPQ convex to compact. And so that are kind of pseudo-Riemannian analogs of the groups of real hyperbolic manifolds. So in particular, these groups for Q equals 1, so these are Lorentzian, this is in some Lorentzian geometry, and these groups were studied by Metz and by Barbeau and Barbeau-Merigot. Okay, so there are many examples because of this. But in fact, so there are also many examples that do not come from deforming. And in particular, what we prove with Jeff and Francois is that if you take gamma to be any Gromov hyperbolic right-angled Coxeter group, then there are many convex to compact realizations of these groups. So more precisely, if we look at the set of representations rho from gamma into GLN plus 1. So representations that are faithful and discrete and as reflection groups, which means that each generator of our Coxeter group is sent to a reflection in a hyperplane in Rn plus 1. So if we look at those representations such that rho of gamma is strongly convex compact in projective space, then this is the interior of this space, of the set of faithful and discrete representations as reflection group. And this has been very explicitly described by Winberg. And in particular, we know that for many values of n, it's non-empty. For instance, if n plus 1 is equal to the number of generators of the Coxeter group. So now this provides many examples with a vast class of abstract Gromov hyperbolic groups, because these groups, for instance, can have arbitrarily large virtual cohomological dimension, but yet many of them are not discrete subgroups of SON1. Okay. So now, is there any question? Otherwise, I'm going to now make a link with Anosov representations to give another reasons why these strongly convex compact groups are nice. Okay, so Anosov representations are nice representations of Gromov hyperbolic groups into semi-simple or reductive Lie groups that were introduced by François Labourie a bit more than 10 years ago. And so initially for fundamental groups of negatively curved, closed negatively curved manifolds, but then it was generalized by Guichard and Winhardt to all Gromov hyperbolic groups. And so these representations have been studied by many GEAR members, and we will probably hear more about them later in the week. So what exactly are they? So we take gamma to be a Gromov hyperbolic group. And then, so we take a representation of gamma into some semi-simple Lie group, but today I in fact want to focus only on PGLN plus 1. And even if I focus only on PGLN plus 1, there are several ways of being Anosov, but today I focus only on one way of being Anosov, which I call P1 Anosov. Sometimes it's called projective Anosov. So this means that there exists two nice boundary maps that go from the boundary of gamma into projective space, and from the boundary of gamma to the dual projective space. So that's our rho equivariant, continuous, and nice, which means they have some extra properties. In particular, they are transverse. Which means that xi of eta is not contain xi star of eta prime for eta different from eta prime in the boundary of gamma. There are dynamics preserving. Which means that xi of the attracting fixed point of some element gamma in the boundary of gamma is an attracting fixed point of rho of gamma in projective space. And similarly for xi star. I don't have any other black pen, I'm sorry. Oh, sorry, thank you. Yes, okay, dynamics preserving, and then there's some extra, oh yeah, that's much better. Some exponential contraction or expansion property condition that can be expressed in several ways. So the original way is in terms of flows on bundles, but there are some other ways. But I will not state it today. So instead, or maybe if you don't like boundary maps, there are some other ways to define Anosov without boundary maps. So P1 Anosov is equivalent by work of Kapovich, Lib, and Porty. And some alternative proof was also given by Bocchi, Potrier, and Sambarino. And I think actually Andras explained this in his mini course last week. So it's equivalent to the existence of two constants such that for any gamma, the first singular value divided by the second singular value of rho of gamma is at least exponential c times the word length of gamma minus c prime. And this should really be thought of as some reinforcement of this quasi-isometric embedding condition. Okay, or if you don't like singular values and you prefer eigenvalues, Raphaël Potrier and myself recently also noticed that this is equivalent to the existence of constants c and c prime, such that for any gamma, the first eigenvalue divided by the second eigenvalue of rho of gamma is at least exponential c times the translation length of gamma minus c prime. So that's the translation length in a Cayley graph. Okay, and maybe just to finish on Anosov representations, one example. We'll see many more examples this week, I think. One example is Hitchin representations. It's initially by studying these representations that François Labourie introduced Anosov representations. So these are continuous deformations of taking a surface group, embedding it into PSL2R in a Fuchsian way, and then embedding PSL2R into PSL n+1R in the irreducible way. So you take this and you deform. So these are Anosov. Okay, so Anosov representations have been studied by many people, as I said, and they're initially defined as having nice dynamical properties, and people saw that they have even more nice dynamical properties. They also have nice topological properties that make them, in some sense, good analogs for these dynamical properties of convex or compact representations into rank 1 Lie groups. So this follows in particular from the work of Labourie, Guichard-Wienaerts, and Kapovich, Leb, and Porty, who did a lot of detailed work on this with some precise analogy. But here we are more interested in geometric structures. So there are geometric structures that are naturally associated with Anosov representations. So for instance, constructed by Guichard and Wienaerts, and also Kapovich, Leb, and Porty. But we would like to have convex ones. So there's a very nice work of Troig and Goldman on this. So we would like to kind of generalize this. So it works well. So here's the theorem. Okay, sorry. So which we prove again with Jeff and Francois. So take gamma to be a discrete subgroup of PGLN plus 1, preserving some properly convex open set omega. Then the following are equivalent. So first, so gamma is strongly convex to compact in projective space. And secondly, gamma is Gromov hyperbolic. And the natural inclusion of gamma in PGLN plus 1 is P1 Anosov. Okay, so first I should say that for gamma that's strongly convex to compact and divides omega, the fact that it's Anosov follows from work of Yves Benoit. Now for this general case, so actually we first proved it for groups that were included in POPQ plus 1, so that projectively preserve some quadratic form. And so this here, in fact, we got this notion of HPQ convex to compact group that I briefly mentioned before. And then, so more recently, we generalized this to all discrete subgroup of PGLN plus 1. And independently, Andy Zimmer also obtained such a generalization. Namely, he proved a similar equivalence, but for some slightly different notion of convex to compactness here. Okay, so now there are some good consequences of this theorem. So the first consequence is this theorem here that I almost erased, which is, sorry, that strong convex to compactness is stable under small deformations because Anosov representations are by work of Labourie and Guichard-Binhardt. Also, strong convex to compactness is stable under embedding into some larger projective space because Anosov representations are, etc. So that's good. We also get convex structures for Anosov representations. So for instance, so for even n, the image of any Hitchin representation into PSN n plus 1 is strongly convex to compact in projective space. And so for n equals 2, this is due to Troy and Goldman. But in fact, and for n equals 2, actually you get divisible convex sets. But here you don't have co-compactness, but you still have strong convex to compactness in any higher dimension for even n. Okay, and also we get new examples. So this is using the fact that Anosov implies strongly convex to compact. But if we use the other direction, we get new examples of Anosov representations. By just taking things that we can prove that they are strongly convex to compact, and then by this theorem we know they're Anosov. So for instance, we get Anosov representations by any hyperbolic, Gromov hyperbolic right-angled Coxeter group, which is kind of nice because until now most known examples of Anosov representations were essentially for surface groups and free groups or groups like this, and here we get a much larger class of groups that can have Anosov representations. So maybe just one word about the proof. So first, why strong convex to compactness implies this. So I already explained why it implies that gamma is Gromov hyperbolic. But then now you know that gamma, by definition, acts co-compactly on the C. So now you can take any orbital map, and you know that it will extend into a continuous injective boundary map from the boundary of gamma into the boundary of C, which is in projective space. So here is how you get your first boundary map. And then you use some duality that strongly convex compactness in projective space is equivalent to convex compactness in dual projective space. So by using this duality, you get a second boundary map. And then what needs to be done is check that these nice properties are then satisfied. Here, these dynamical properties. Okay, and very briefly, the other direction. So if we start with a group here that preserves some properly convex open set omega, and that's Anosov. So we have our convex set omega, and we would like to find a C on which the action is co-compact. So what we do is we use what we have, the Anosov boundary map. So the image of the Anosov boundary map is actually contained in the boundary of omega. And so one can just then take the convex hull of this image of the boundary map. So this will be our C. And then the work is to use the strong dynamical properties of Anosov representations to prove that actually the action of gamma on C is co-compact. Okay. But so now to finish, I would like to talk about other notions of convex compact, because if you look at this picture, it doesn't seem quite complete, right? Because we here have strongly convex compact groups, so that are, it's nice because they're P1 Anosov and they're stable. So that's great. But it's all hyperbolic groups. So it would be nice if we could also have some notion of convex compactness for non-hyperbolic groups. So let's do this. So now if we want to allow for non-hyperbolic groups, we should remove this strong assumption that there's no segments in the boundary of omega, because we saw that this was really the assumption that forced hyperbolicity. So we can just do this in a very naive way. So let's call this now naively convex compact. So we just remove this assumption. So that's good. That's a class of groups now that contains non-hyperbolic groups, because it contains all those that divide some omega. So that's my new class of groups. The naive convex compact ones. But unfortunately, it is not stable under small deformation. So it's not such a good class after all. And let me just give you one example. So let's do a very simple example of a cyclic group in PGL3. So we take a cyclic group generated by 2, 1, 1 in PGL3R. And I claim that this group is naive convex compact in RP2. So why is it naive convex to compact? Well, because it preserves this omega, which is a triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's omega. And actually, it preserves all the lines through this point like this. So I can now take C to be any smaller triangle like this. This is a closed convex subset of omega, and the action is co-compact on this. So it is naively convex to compact. But not if we deform slightly. So we can deform. And instead of having this identity block, we can make it a small rotation block. So the group generated by 2 and cosine epsilon, sine epsilon, minus sine epsilon, cosine epsilon. And this group now does not preserve any properly convex open subset of RP2, because, so it fixes this point, and it now acts by rotation on this projective line. And so you can see the picture, there's no way you can preserve a convex set here. So this shows that it's not stable under small deformations. But maybe you're a little bit frustrated because this is such an elementary example with a cyclic group and in PGL3. So in fact, you can make this example irreducible. In PGL4. And now what you will do is gamma will be a free product of this Z embedded into PGL4 with some Z mod 2Z. And this is up to finite index, just a free group on 2 generators. Okay. So yeah, so in general, it is not stable in the small deformations. And also, this shows that here the naive convex to compact groups for hyperbolic ones are strictly larger than the strongly convex to compact ones. Yeah. Okay. So this doesn't work so well. So instead, we could try to use the second definition. So, okay, naive convex to compact was this definition. But instead, now we use the second definition. And this will give us something that we find very nice. So we feel that it deserves to be called convex to compact without any adverb, because it's like the ultimate notion. So convex to compact is now with the second notion. We want this quotient to be compact, where this is the convex hull of the limit set. The only little problem is that what is the limit set? It's the set of accumulation points of some gamma orbit. But now, if the set is not strictly convex, this depends on the gamma orbit. And you can see it very well on this example, because if I take x here, then the accumulation points of the gamma orbit of x are these 2 points. So it depends on x. This is not very good, and it's part of what makes this bad behavior here. So what we want to do is instead have something canonical and remove the dependence on x. So what we do is we take now all we take all accumulation points of all gamma orbits. So of gamma x for all x. Okay, and we call this now the full orbital limit set. Okay, so this gives a definition now for convex to compactness without adverb. And note that this bad example here does not satisfy my good red definition. So this is not convex to compact. Why is it not convex to compact? Because if I take all the accumulation points of all the gamma orbits, I get this whole open segment plus this point. So I take the convex hull of this, and I get the whole of omega. But the action of gamma on omega is not co-compact. So this is not co-compact in convex to compact in RP2. Okay. And so now this is a good definition. So okay, I can rewrite the theorem I had partly erased. I can just remove the strong. So convex to compactness is stable under small deformation. Again, convex to compactness in RPN is equivalent to convex to compactness in dual projective space. If you are convex to compact in RPN, then you are convex to compact in any bigger projective space. And also, if you are convex to compact and Gromov hyperbolic, this is equivalent to being strongly convex to compact. So now the picture is like this. So I have my nice class of convex to compact groups that here coincides exactly with this strong convex to compact, and here goes like this. So this is convex to compact. Okay, so now to finish, just a few comments. So first, exactly as before, these properties give many examples, because we can take known examples. For instance, here, those gamma that divide some omega, which is not strictly convex, so gamma is not hyperbolic. And then we can embed these groups into some larger PGLN and projective space, and then we can deform there. And in many known examples, it's actually possible to have non-trivial deformations by bending, in particular in the examples of Benoit and later examples. But there are also other procedures to construct more examples of convex to compact groups. So in particular, we have some procedure to take free products. When you have two convex to compact groups, you can conjugate one and then take a free product and get something convex to compact in this way. And like this, this gives even more examples, in particular examples of non-hyperbolic Coxeter groups that are convex to compact. So just to finish, quick idea of the proof of this. So we have our convex, we suppose that we start with something convex to compact. So we have the quotient manifold. So that's omega mod gamma. And inside, we have our co-compact convex core. So that's C gamma omega mod gamma. But typically, the boundary of this convex core is not strictly convex in general. But what we prove is that gamma convex to compact is equivalent to the fact that we can find some larger C mod gamma. So here, sorry, that's my C mod gamma. So which is still closed and convex, so which is still compact and convex. And now with strictly convex boundary. And So we can construct by hand this bigger set. And now this is very good because now we can just reduce to the theory that was developed by Cooper, Long, and Tillman for the holonomic groups of such convex projective manifolds with strictly convex boundary. So we can use Cooper, Long, and Tillman. Okay. And now, so to finish, let's just have a look at this diagram again. So here we had the very nice strongly convex compact groups that were also the P1 Anosov groups. Here we have this larger class of convex compact groups, so which in some sense are generalizations of P1 Anosov. And so I would like to finish on a question, which is, can we describe and characterize the dynamical properties of these generalizations of P1 Anosov representations? And okay, I will stop here.
There's tea and coffee and some things to eat back where you registered back in the courtyard. In particular, if you signed up for the banquet, if you would please talk to Mandy there and confirm what you ordered and pay up